In the past few videos, we've seen how the constants a, b, and c can be used to help us identify where the graph intersects at the x or y axes, or where we might have a minimum or maximum. We're going to do the flip version of this in this video. We're going to purposefully modify a, b, and c constants, change them, increase them, decrease them, change the signs of them, and see if we can identify patterns in the graphs that appear from them. So in the easiest case here, we're going to look at just the a constant. So most of the examples we've seen before, we kept a to be +1 or -1 and just varied b and c. In this case, we're going to vary our a constant and keep b and c 0 so we can focus on the effects there. Here I use x squared as my solid red curve here as a reference point. And then we have 2x squared, 3x squared, 4x squared, 5x squared, getting tighter and tighter. And this makes sense because at any x location, the larger your a value is, the larger your y value will be. And then I went the opposite direction, all right? Again, smaller and smaller, 1/2, a third, a quarter, and then a fifth. So we see the shape of the curve is dictated by this a constant. And we see that here, a is increasingly going from a fifth to 1x squared to, what would I go up to, 5x squared, right? So you can see if you want to make it a tighter curve or wider curve, we can change our a constant to accomplish this. It's useful to think about this also in terms of a negative value. So I just put a negative sign in front of all these terms. Again, I have -x squared as my reference point. The tighter, just flipped, is a larger a value, a larger negative a value, right? So there, the tightest one we have there is -5x squared. The widest one we have here is -1/5 x squared. So again, as our negative a value gets larger, we have a tighter graph, right? So now, that gives us pretty good context of how the a constant affects things. Now, it's important to know that a doesn't work independently. It works with the b constant as well, and we'll see the combination effects in the next couple slides. All right, so now we're going to take a look at the b constant specifically. So I'm going to set my c constant to be 0 and my a constant to be 1, just to keep things simple. And we're going to see something interesting. So we're going to use y equals x squared as our reference graph, and then just change the b value. So I'm going to go b equals 1, b equals 2, 3, and 4. So I get x squared plus x squared plus 2x, plus 3x, plus 4x, and so forth. And what we see is the shape of the graph remains the same, right? It doesn't get tighter, doesn't get wider. And that makes sense because my a constant is not changing across all these examples. It is shifting. It is shifting to the left and downwards. So it's not just shifting in one direction, it's shifting in both directions. If I change the b values to negative, we see a very similar behavior as well, right? So again, here's my reference x squared term. Then I shift it by, so I have -x, -2x, -3x, and -4x. And it just shifts to the right. So it's to the right and downward as well. Now, it would be nice to know why it's shifting and how much it's shifting to kind of have some reference of how b is directly influencing this. Luckily, we have a way to look at this. What's a good way to see how a parabolic graph is shifting? Well, a good reference point is the min or max. So we can look at the minimum in this case because it's x squared. It's not -x squared. We can do the same thing for -x squared graphs. And I'm going to look at the minimum. And so if this is my specific case, you can generalize this method and look at ax squared plus bx plus c, but I just want to look at for this specific example. So I have y equals x squared plus bx. I can find the minimum of this graph, and generalize it to all minimums of these graphs. And what I want to do is be able to overlay a secondary graph that hits all the minimum points. So I feel like this is a pretty interesting method to identify all minimums of this kind. So if I take the derivative of this equation, y equals x squared plus bx, I get derivative of x squared is just 2x. The derivative of bx is b. And I set it to 0, then I'll have the minimum. Right? In the past, we've done this to identify the x location. In this case, I want to find a relationship between x and y. So I want to find the relationship between b and x, actually. So you'll see how this looks like. So if I set this equation to 0, all I get is b is equal to negative 2x. Right? Fairly simple. Then I take this value and I plug it back into my general equation here to identify how x and y are related once you're at the minimum. So I have x squared plus b, which is negative 2x, times x. That's what this term, this section is here. Then I just solve for this, right? I got x squared minus 2x squared equals negative x squared. So what I'm going to do is I'm going to graph y equals negative x squared. You see that you hit all the minimum points. And if I do the same thing to this graph here, you'll hit all the minimum points as well. Now, the graph that hits all the minimum or maximum points will change if you change what A is or change what C is. But for all equations where A is equal to 1 and C equals 0, they fall on this graph. So we can have a very good understanding of how changing the B term would affect this. Now, this is really important in engineering because from a physical standpoint, there are many physical systems where you can specifically change components that change the A term, change the B term, or change the C term. So we'll see where the real predictive ability of understanding these kind of graphs really come into play when we look at the application videos. So here we have 8 equations. They look fairly similar, right? So I chose arbitrarily A to be 1, B to be 2, and C to be 3. And then I swapped out positive and negative signs in front of them, depending on which combination of equations that I was looking at. So I have all 8 combinations here with plus or minus. And the 1, 2, and 3 are arbitrarily selected. I want you to show that it doesn't matter if the constants are different from each other. They don't all need to be 1. They don't need to be 0. This pattern works regardless what the constant is. So what we're going to look at first is how the C constant affects things. And then we'll look at how the combination of pairings are affected by the sign changes. Okay. So first, the top 4 equations, examples, have positive 3 as our C value. And you can see that as the y-intercepts all at plus 3. And in the bottom, you see negative 3. And you see that in the y-intercept of negative 3. The C value just changes by shifting the graph vertically, right? And this makes sense because the C value directly is related to our Y value here. It's the constant shift, right? So if you want to shift your graph up by 5, you just put a 5 value for C. All right, so I paired them in the way that the A value is the only thing changing, right? So we have positive B's, positive C's, but the A value is plus or minus. Negative B's, positive C's, but the A value is positive or negative. And you see that you don't get a mirroring effect directly. You get a kind of a diagonal mirroring effect. You do have the same y-intercept because the C value is the same. Now, if you do want to mirror across the x-axis and then mirror across the y-axis, we can see what sign changes would be required to do that. So if I look at this graph here, this solid red line, I get x squared plus 2x plus 3. If I want to mirror this across the x-axis, I need to put a negative sign in front of everything. So I need a negative x squared minus 2x minus 3. And that makes sense because that will essentially put a negative sign on the y, basically flipping the y value of each x location. So can we see that mirrored across? Well, here we go. Negative x squared minus 2x minus 3. So all the signs are changed in this pairing if we compare it. Right? So this dashed purple line here we can see is mirrored across the x-axis. You can do this for all of the cases. So if we look at this case here, the one that will mirror is this dashed blue. So we can look at the signs in front of our values. So we have a positive a, negative b, positive c. In the dashed blue here, we have the exact opposite. Negative a, positive b, and a negative c. Right? So you can see that's mirroring across the x-axis. We can mirror across the y-axis. Now, if we want to mirror across the y-axis, all we need to do is swap out the b sign, right? So if I look at this red one here, the one that mirrors it across the x-axis is this one right here. So that's x squared plus 2x plus 3. This one is x squared minus 2 plus 3. And why is that the case? Well, this is x squared, so the sign won't affect the a value here. This is just x, so the sign will directly influence and mirror across the y-axis if this sign is changed. You can look at a different case, right? So this dashed line and this dashed line are mirrored across the x-axis. So negative x squared plus 2x plus 3, negative x squared minus 2x plus 3. So only thing that's different between these two are the b signs right here. And then same thing on the bottom one here. So you can see how you can move your graph across the axes by changing the signs, and you can see how you can shift the graph vertically by changing your c value. And here I'm looking at all the negative x squared components all linked up here, so you can see the purple and the blue can be are directly mirrored across the y-axis, and then if we shift them up by changing the c value, then we get this green and red dashed lines, which are also mirrored across the x-axis. Same thing is true for the positive x squared or positive a values, right? The solid red and solid green are mirrored across the y-axis by changing the b sign, and then shifting it down by changing the c values to -3 from +3 to -3, and that's also going to be mirrored across the y-axis. So, you know, all these little nuanced changes of increasing or decreasing a, b, and c, or changing the sign of a, b, and c, and seeing how it mirrors across the different axes is very useful when you're trying to compare different systems that you know the equations of, or if you want to interpret data and you know the values or know the difference between the a, b, and c constants if they're described by a quadratic equation.